This is a realistic and clean Gaussian splatting model. It is free of messy, floating artifacts, and the clarity remains impressive even when zooming in close. In today's video, we will cover every step, including data acquisition, Gaussian splatting generation, editing, and rendering. The data used to generate the Gaussian model in this video was captured using a 5-year-old iPhone. Most importantly, all the software we are using here is free. We use the Blackmagic camera app for data collection, MipMap Desktop for generating the Gaussian splatting model, and SuperSplat for editing and generating the rendered video. You do not need to spend a penny to replicate the workflow in this tutorial. I will explain every step in as much detail as possible. If you like this kind of content, please click the like button below and subscribe to our channel to be the first to receive our latest content. Let's get started. First, open the Blackmagic camera app. We will enter the settings interface and reset all settings to configure the software from scratch. Switch to the record panel under the settings tab. Select Codec. H.264 encoding has the best compatibility, meaning you can view the final video normally on most devices and software, but it limits the maximum frame rate in 4000 mode to 30 frames per second. H.265 encoding is more efficient, allowing for 60 frames per second in 4K mode. With the same image quality, the resulting video file size is smaller, which saves storage space on your phone. Here, we select the more efficient H.265 encoding. Set the bitrate to the maximum. Bitrate affects video quality. While some minute differences may not be distinguishable to the human eye, they can have an impact on stereo vision algorithms. Confirm that the resolution is set to 4K. Enable time-lapse recording. This is a very useful setting. The data we use for Gaussian reconstruction does not require every single frame of the video. This setting allows us to reduce phone heating during recording and significantly reduces the video file size. For example, if I set it to save 1 frame every 10 frames, the video file will be nearly 10 times smaller. You might be curious, why do we use the 60 frames per second mode? Because the 60 FPS readout mode reduces the imaging distortion caused by rolling shutter, making it match better with the mathematical model established by the Reconstruction software for the camera, thereby resulting in a better model. Next, switch to the camera panel and turn off lens correction. Reconstruction software mathematically models the camera's lens distortion. The built-in distortion correction function of the camera often destroys the match between the imaging process and the mathematical model of distortion modeling, so make sure to turn it off. Lock the camera to shoot horizontally. Switch to the audio panel. We do not need the audio recorded during shooting, so you can turn it off. Mastering the exposure triangle is the first step to great photography, but it is even more critical if you are doing 3D reconstruction. Let's break down how aperture, shutter speed, and ISO affect your results. First, aperture controls your depth of field. A large aperture, like f1.4, lets in more light but blurs the background, whereas a small aperture, like f, keeps the entire scene sharp. When using a phone for 3D reconstruction, the approach changes slightly because you cannot mechanically adjust the aperture. However, you must be aware that the different lenses on your phone have different natural depths of field. Second, shutter speed determines motion blur. Slow speeds can cause moving objects to look blurry, while fast speeds freeze action instantly. Third, ISO controls the sensor's sensitivity. A high ISO allows you to shoot in the dark, but adds grainy noise to the image. Now let's switch to the recorder view. Click the stabilization icon at the bottom and turn off camera stabilization. Digital stabilization of the camera is achieved by panning, zooming, and rotating the image. These operations change the camera's intrinsic parameters, specifically the focal length and principal point. Keeping camera parameters constant during the entire shooting process makes subsequent reconstruction more stable and avoids overfitting during camera parameter calculation, which can affect model quality. It has always been the best practice in photogrammetry. Of course, turning off stabilization will bring about issues with shooting, jitter, and blur. If you have a handheld gimbal for your phone, using the gimbal's physical stabilization will greatly alleviate this problem. Later in the video, I will also mention how to avoid having blurred video frames participate in the reconstruction. Phone cameras typically have 3 lenses. Each has its pros and cons. The ultra-wide lens is a fixed focus lens, which means its shooting range is almost always clear and will not be blurred or out of focus. More importantly, it does not need to focus, ensuring that the camera's intrinsic parameters are consistent throughout the entire shooting process, or even after restarting the camera. The manual focus settings in the software have no effect on it at all, which is an excellent trait for reconstruction tasks. However, its lens distortion is more complex, and the image quality is not as good as the other lenses, especially when ambient light is insufficient. The wide-angle lens has the best image quality, but cameras with this lens are equipped with sensor shift stabilization. It seems this stabilization cannot be completely turned off through software settings, which may bring some changes to the camera's intrinsic parameters. Also, as you can see with nearby objects, the subject can easily become blurred and out of focus as the focus distance changes. The telephoto lens also has this problem. We expect to keep camera parameters constant during the shooting process, so we need to fix a focus distance. Then, keep a close distance to shoot the object, avoiding large variations in shooting distance. To set the focus distance, you can first switch to autofocus and then cancel autofocus to lock the corresponding focus distance. If you need to shoot at different distances, you can collect data in multiple batches, using different focus distances for each, and then group the cameras during reconstruction settings. To prevent motion blur during shooting, we set a faster shutter speed and keep it constant. It is recommended that the shutter speed is not slower than 1/500th of a second. Click the ISO icon and set it to the minimum value to get better image quality. If this setting makes the image too dark, you may need an environment with better lighting. Then switch to the white balance setting. Adjust the color temperature until the color seen on the phone is closest to the color seen by your naked eye, and then lock the white balance. Once all the above settings are completed, you can ensure that the camera's intrinsic parameters remain constant during the data collection process. Click the Start Recording button to begin recording. This is the video used in this tutorial. It has not been sped up. The video only records frames at intervals. When shooting, try to keep the camera at an oblique, downward angle. Having too much background and sky enter the camera frame will make the final result messy and will also cause more computation to be spent on the background, which we do not care about. When shooting, try to orbit from different angles, moving as slowly and smoothly as possible. You can orbit around a local part of the object. Not every photo needs to contain the whole object, but ensure that all parts of the object are captured. There is another good method. Imagine if the model were already generated, from which angles would you view this model? Then it is best to include similar angles when shooting. This method of setting up a smartphone for shooting is not only applicable to Gaussian splatting, but also to photogrammetry. MipMap software is not only a Gaussian splatting generation tool, but also one of the leading professional photogrammetry solutions on the market, offering the fastest processing speeds and highest quality mesh outputs. Let's open the MipMap software to generate the Gaussian splatting model. If you encounter problems registering an account or using the software, you can check our previously recorded detailed tutorial. The link is in the description below the video. Click Import Video, select the recorded video file, and enter the video frame extraction interval. Set the corresponding extraction parameters. The free version of MipMap supports reconstruction of up to 500 photos per single task. After setting up, click Confirm. Wait for the extraction to finish. The extraction here is relatively simple and fast. If your recorded video has many blur issues, you can use the SharpFrame web app to extract video frames. However, please note that if you plan to use this tool, you will need to select the H.264 codec in the video encoding settings. It will automatically select clear video frames, and you can set the interval and quantity of frame extraction though it also requires more processing time. Back in the MipMap software, click the camera button to enter the camera parameter setting interface. Setting the correct camera focal length parameter as an initial value can help with camera pose recovery. Click the calculator icon to perform focal length unit conversion. We use the telephoto lens for shooting, and it's 35mm equivalent. Focal length is 65mm. We use the 35mm equivalent focal length to convert the pixel focal length. Click Confirm to complete the camera parameter settings. Select Ultra High Model Quality. Turn on the Gaussian Splatting result switch. Each type of result takes a certain amount of time to compute. If you do not need them, turn off the 3D mesh and point cloud results. Click Start Reconstruction. Just wait for the model generation. Before recording this tutorial, I had already generated this model, so let's switch to the completed model task. In the camera pose interface, you can view the camera positions during shooting and the sparse point cloud of the scene. You can adjust the size of the camera icons. Click the GS button to switch to the Gaussian Splatting model. You can explore and browse the details of the model in this interface. Click the View Product button to open the Gaussian Splatting result model. We will use the SuperSplat tool for editing to make the model cleaner. Click the File menu, Import Model, and select the Apply result we generated. By default, you will see the point cloud of the Gaussian result. Click the button on the right to hide the Gaussian point cloud. Sometimes, when you drag to browse the model, it does not rotate as you expect. This affects the model browsing experience. At this point, you can adjust the model's coordinate system. Here, we first set the z-axis rotation to 0. Rotate the model to align the coordinate system diagram in the upper right corner of the model. You can see that the model does not align well with the coordinate axis and looks a bit tilted. It needs to be rotated by some angle along the x-axis. You do not need to know the specific angle. Click in the input box for the x-axis on the left and drag left or right until the model looks straight, then release the mouse. After adjusting the coordinate system, the rotation operation is much smoother. Left-click to rotate, right-click to drag, and use the scroll wheel to zoom in and out. You can view the model from all angles. To edit the model, you first need to select the Gaussian spheres you want to edit. Now, let's look at its rich selection tools. These selection tools are easy to understand. The rectangular marquee tool selects, and the selected Gaussian ellipsoids will be highlighted in yellow. You can press the Delete key on the keyboard to remove the selected Gaussian ellipsoids. However, note that the geometry of Gaussian ellipsoids has two display states. In center mode, the selection is penetrating, meaning all Gaussian ellipsoids within the selection range from this viewing angle will be selected. In ring mode, the selection operation will only select the nearest Gaussian ellipsoids in the viewing direction and will not select the remaining occluded Gaussian ellipsoids. There are many other selection tools. For freehand shapes, use the lasso select. Just draw the outline you want directly on the screen. If you need precise, straight lines, switch to Polygon Select, click to place your points, and double-click to close the shape. For a more organic feel, try the Brush Select. This lets you paint your selection. A handy shortcut here is using the bracket keys on your keyboard to quickly resize the brush. To clean up messy noise or floating artifacts, the Flood Select is a lifesaver. Click anywhere to auto-select an area and use the slider to adjust the sensitivity. It's perfect for isolating those stray floaters. Finally, for 3D control, there is the Sphere Select. When you click the Set button, a sphere will appear. Then adjust its size and position to select everything inside that volume. Click Invert Selection in the Selection menu to select all Gaussian ellipsoids outside the sphere and delete them. These selection tools are based on spatial position. In addition to these, there are selection tools based on histogram statistics. Open the Splat Data panel. Select the required statistical metric from the drop-down. Some statistical metrics may be very concentrated in a very small range. In this case, turning on log scale can make the distribution more intuitive. Drag to select in the histogram area on the right. With these tools, you can flexibly choose tools to edit and process the model. After the model cleaning is complete, you can set specified viewing angles as keyframes to constrain the trajectory and camera orientation of the model showcase video. Once finished, you can choose to share the model publicly with the community. After sharing the model to the community, the model will first be displayed following the trajectory you edited. But of course, you can also use the mouse and keyboard to interactively browse the model. I have placed the model link for this tutorial in the description below the video. You can also export the edited model. You can also render it as a video for sharing, just like the clip at the beginning of this video. Okay. That covers everything for this video. Your likes and follows are our greatest support and our biggest motivation to produce and share tutorials. Thank you for watching.